Okay, today we're going to do the video for 5.5, all for one, and one for all, I believe, if I remember right. And anyway, if we were in the classroom, I'd be giving you these coordinate planes you guys see right here, slide 6, 7, 8, 9, 10. And how many more did I have there? 11, and even this last one where I have some boundary lines on it, and we will have done those boundary lines previously, and we're going to use this for our system of inequalities for the very last problem. So I will give you access to a link that has all these graphs on it, so we can do this remotely. So let's get going today. It's a great activity. So slideshow from current slide. And here we are, 5.5, all for one, one for all, a solidify understanding task. So Carlos and Corita have found a way to represent combinations of cats and dogs that satisfy each of their individual pet sitter constraints. But they realize that they need to find combinations that satisfy all of the constraints simultaneously. Why? All right, well, think about that. All right, these are constraints that have to do with the well-being of the animals that Carlos and Clarita are taking care of. These pets right here. Okay, and let's review what the constraints we have worked with so far are. I think there were 4 of them, and the first constraint was a cost constraint because dog runs, if I remember right, then they cost $80. And cat pens, they were a lot less than that. I can't remember, $32 or something like that, you know. And money or cost of these pens and dog runs would be a constraint. Number 2, space. They have to have a place to put these dog runs and cat pens. So space is a very important constraint. Number 3, feeding time. All right. They have to have the time to feed these animals. They're going to be with them all day. And number 4, pampering time. And you guys know these pets, look at these cute little pets right here. They need attention. All right, that's pampering time. So these are all constraints. Now, why must we satisfy all of the constraints simultaneously? Well, if we're not meeting any one of these constraints, then we're not taking care of these animals the way we need to. So how did I write that? If Carlos and Clarita cannot meet any one of these 4 constraints, they will not be able to appropriately care for their animals. Oh, that's well said. So number 1, begin by listing the system of inequalities you have written to represent startup costs and space pet sitter constraints. And today, anything we have that has to do with a dog, we're going to use an X for. And anything that has to do with a cat, we're going to use a Y for. And here's the constraints, startup costs and space. And I know we've done this before, but now we've got to make sure this kind of stuff is automatic. We're solidifying our understanding, meaning you need to be able to read this paragraph and come up with an inequality in standard form that represents it. And that's what math is about, making us more concise, more efficient. So Carlos and Clarita plan to invest much of the $1,280. So let's start with that, much of. That sounds like an inequality to me, and could I say much of $1,280 would be less than or equal to? Less than or equal to what? $1,280. They earned from their last business venture to purchase cat pens and dog runs. It will cost $32 for each cat pen. So that's 32 times Y, the number of cat pens, plus, and how much do those dog runs cost? And $80 for each dog run, plus 80 times X, the number of dog runs, plus 80x. And there is our inequality in standard form for the cost constraint. Pretty easy. Now the space constraint. Cat pens will require 6 square feet of space, so that'd be 6 times the number of cat pens, 6y. While dog runs will require 24 square feet of space. Those are a little bigger, so let's go plus, and that's going to be 24 times x, the number of dog runs. All right, Carlos and Carita have up to 360 square feet available. So up to, that implies again less than or equal to what? 360. Less than or equal to 360. And this is our inequality in the standard form that represents the space constraint right there. Okay, number 2. Find at least 5 combinations of cats and dogs that would satisfy both of the constraints represented by this system of inequalities. How do you know these combinations work? So let's go back, and that's what we were talking about up here. If Carlos and Clarita cannot meet any one of these 4 constraints, and right now we're just talking about the first 2, then they will not be able to appropriately care for their animals. So we're beginning with our first 2 constraints right here, and we need 5 combinations of cats and dogs that would satisfy both of the constraints represented by this system of inequalities. All right, so what we're going to do is we're going to graph this system of inequalities and then look for ordered pairs that will work. So graph the system of inequalities. Okay, now 80x plus 32y is less than or equal to 1,280. That was our cost constraint right there, because the dog runs were costing $80 and the cat pens were costing $32, and Carlos and Clarita had up to $1,280 to spend. So if I'm going to graph a boundary line for that constraint and that inequality is in standard form, I'm going to use intercepts. So standard form to me always implies intercepts. And to find the intercepts easily, I'm going to do a cute little table. And in this table, I'm going to let x equals 0 to find the y-intercept, and then I'm going to let y equals 0 to find the x-intercept. So I always start my table just like that. And then I break out my calculator, because to find the y-intercept where x equals 0, it's just simple arithmetic. All right, so now take a look. If x equals 0, 80 times 0 is gone, that's 0, and I'm left with 32y is 1,280. So to solve for the y, I just divide the 1,280 by 32. 1,280 divided by 32, and I'm getting 40. So the y-intercept of this constraint is 40. What's the x-intercept? So now we let y equal 0. So if the y is 0, I have 32 times 0 is 0. And I'm left with 80 times x is 1,280. So to find the x, I divide the 1,280 by 80. 1,280 divided by 80 is 16. So the x-intercept is 16. So let's plot our y-intercept. Now I don't see 40 on here, so I'm going to have to approximate this. So what are my hash marks? Are those 3? Let me see. 3, 6, 9, 12, 15. Yes, they are. So I'm up here at 30, 33, 36, 39. So 40 would be about right there. And that's just my best approximation. It's not perfect, but it will get the job done. And now my x-intercept is 16. I also don't see 16 on my x-axis, so I'm going to approximate where it is. And now these hash marks are all worth 1.5. 1.5, 3, and so on. So to get to 16, well, at 15, that would make this 15.5, or excuse me, 16.5. So 16 would be what? About right there. Now, is that perfect? It's not perfect, but it's pretty darn close. And now I look at my inequality, less than or equal to. That means my boundary line has to be solid for the equals. So now I get my ruler out and I take my pencil and I do a solid segment between those two intercepts. And again, use a ruler so it's perfect. Now, let's do the same thing for, let me see, that was cost, this is space. Because the dog runs takes 24 square feet, the cat pens take 6 square feet, and we have up to 360 square feet. Okay? So, shading the plane. Oh, by the way, shading the plane. Okay. Now, again, this is a boundary line right here. But again, this less than or equal to, we're shading half of the plane here. All right? And now, by the way, there's a quick way to do this. Okay, see that plus 32y? The last step, if I were to solve for y, would be to divide by 32. And if I divide both sides of an inequality by a positive number, it will not affect my inequality. So it's still going to be less than or equal to. So if y is less than or equal to an expression in terms of x, that means I would shade below this solid line. And remember, it's solid because of the equal sign. Now, again, I want to practice, so let me go back. But remember, we're eventually going to shade below it, but let's practice here. All right? Again, if I can solve this for y, I'm putting this inequality that's in standard form in the slope-intercept form, and I'm going to end up with a y is less than or equal to, which is going to make it very much easier for me to see which side of this boundary line I'm going to shade. So the first thing I would do is get rid of the 80x's. So I'm going to subtract 80x from both sides. And that does not affect my inequality. So I'm going to bring down the less than or equal to. I put it over here. That's okay. And 80x minus 80x is gone, leaving 32y's. And on the right, I cannot combine these two terms, so I have to write them in expanded form. And I'm going to start with my x term first, so I go that slope-intercept of y equals mx plus b. So I have negative 80x plus 1,280. Now to solve for y, we have to undo this multiplication by 32. So let's divide both sides by 32, and that's dividing every term by 32. 32 is positive, so my inequality will stay less than or equal to. And now on the left, my factors of 32 cancel, leaving my y. And on the right, I have a negative over a positive is negative. And then I just need to reduce the fraction 80 over 32. So what's the biggest number that goes into 80 and 32? I think it's 16, because doesn't 16 go into 80 5 times? And doesn't 16 go into 32 twice? And by the way, you could on your calculator go negative 80 divided by 32 and hit equals, and your calculator will give you a decimal that you could convert to this fraction right on your calculator. But I like to practice doing this stuff without the calculator. Now, don't forget your factor of x. So that's negative 5 halves x. And then we have plus, and I'm going to punch that out on a calculator. 1,280 divided by 32. 1,280 divided by 32, and that's a 40 plus 40. So let's check things out now here. This is cool. My y-intercept would be 40. Well, that is y equals 40 right there. And my slope is negative 5 over 2. All right? And again, and it's hard to see the way this is scaled, but we'll talk more about that because there's lots of ways to do this. But again, I'm dropping 5 and I'm running 2, which is going to put me about right there every time. Okay, so let's shade below. And again, I'm shading below because of the y, which measures vertically, is less than or equal to this boundary line. So the boundary line is solid because of the equals, and we shaded below because y has to be less than or equal to that boundary line. And that's how you do this. Now, let's do the same thing with the 24x plus 6y is less than or equal to 360. And again, I already know that I'd be shading below the boundary line, but first, let's go ahead and get our boundary line. So again, my cute little table right here, and I'm going to go a y-intercept and an x-intercept. So at x equals 0, I have 24 times 0 is 0, and I'm left with 6 times what number is 360? So let's just go 360 divided by 6. And I think that's going to be what? A 60? Yeah, there it is. All right. And now if y is 0, 6 times 0 is 0. So I'm left with 24 times what number is 360? So let's take the 360 and divide by the 24. And that one I get a 15. So for my boundary line, for my space constraints right here, my y-intercept is 60, and that's all the way up here at the top. We can see that, didn't have to count them. And my x-intercept is 15, and I can see that right there. So this is going to be absolutely perfect. Now get out your ruler and set up between those two intercepts, and make sure, because of the equals, we do a solid segment again, just like that. Now, because of this plus 6 that I'm multiplying the y by, I already know I'm going to eventually shade below that boundary line. But let's solve for y just to double check everything. So we're going to get rid of the 24x's on the left. Minus 24x, minus 24x. And that will not affect the inequality. 24x minus 24x is gone, and we're left with 6y is, and again, we cannot combine those, so let's write this negative 24x plus 360. Excuse me. Now, we have to undo multiplication by 6, so let's divide every term by 6. And we divided by a positive, both sides, so that will not affect our inequality. And on the left, the factors of 6 cancel, leaving that factor of y. So y is less than or equal to, our conjecture was right, we're going to shade below it. And now let's simplify negative 24 over 6. And let's try this without a calculator. A negative over a positive is negative. And if you simplify the fraction 24 over 6, there's my fraction bar. And what number goes into both? Hey, doesn't 6 go into 24 4 times? So that would be a 4 over 1, which I actually could have written as just 4, but I had the fraction bar, so 4 over 1. Then I can see slope really easy too. And don't forget that factor of x right there. And then 360 divided by 6. Well, 6 times what? 6 is 36, so 6 times 60 would be 360 plus 360. Or plus 60. So make sure, if you're not sure, check it on a calculator. Okay? And now look at what we see. Y is less than or equal to negative 4 over 1x, or negative 4x plus 60. That less than tells me I'm going to shade below this solid red boundary line right here. And now look at how I do this so I can clearly see a double shaded region. Do you see how I did oblique segments for the first shaded region? Now I want the segments underneath the red boundary line to not have the same slope so I can see. Now watch. So I did them horizontal here. Now with that, can you clearly see the double shaded region? Very good. All right, now what did they ask us for again? I think they asked us for 4 or 5 points that will work for both constraints. And those points would have to be in the double shaded region or on this part of the blue segment. And then when you get to that intersection point, it could be on this part of the red segment. So we need to find those points. So dogs. Well, here's what I do. This is always my strategy. I would love to be able to use the same x coordinate for every point. So I'm going to pick an x value. Okay, so I use x equals 6 right there. So all my x's are going to be 6's. And I'm going to use this point, and then I'll just use, how about this point? And this point? And this point. Now I don't remember if they asked for 4 or 5, but I go one more would be 5. And apparently they asked for 5. So there's the points. Now these ordered pairs will work, and these ordered pairs will give me the number of dogs and the number of cats that I can deal with the given constraints. And again, here's where I pick these vertical points right here. What's the x-coordinate of every one of them? 6. So all my x's are 6. And now what are my corresponding y values? Well, on that bottom point, remember, every hash mark here is what? 3. So that's going to be 3. That's going to be a 6. And then the next one would be a 9. And then a 12. And then a 15. And then an 18. So these are the 5 ordered pairs representing the number of dogs and the number of cats that will meet our 2 constraints. These are options that Carlos and Clarita could deal with. Wow, isn't that cool? Now 3. Find at least 5 combinations of cats and dogs that would satisfy one of the constraints but not the other. For each combination, explain how you know it works for one of the inequalities but not the other. So we're going to go back to our graph of the system of inequalities right here. Now, remember when we found the 5 ordered pairs that work for both, we were in the double shaded region. So if I want 5 ordered pairs that are going to work for only one of the 2 constraints, I need 5 points that are in one of the shaded regions, not the double shaded. So I need something on or below the red line, but above this blue boundary line. And I'm going to do the same strategy. I would try to pick points that have the same x-coordinate. So let's see what I did. Oh yeah, looks like I'm going to go x equals 3. And then put a point here. And then a point there. And then a point there. And there's 4 and I need 5. And I can be on the boundary line, so I'm going to put another point right there. Okay, now look at this. Every x is 3. And now let's put the corresponding y coordinates on our table right here. So what's the y coordinate of this point? Well, if this is 30, 33, that would be 36, 39, and the pattern continues, 42, 45, and 48. And these are the ordered pairs that would work for the space constraint, but not the cost constraint. So these ordered pairs are not an option. Okay? Carlos and Clarita cannot have 3 dogs and 36 cats. Okay? It won't work. All right? Because what? They don't have the money. Okay, cool. So space, that worked. Cost, I'm sorry, Carlos, Clarita, but you don't have the money for that. All right, number 4. Shade a region on the coordinate grid that would represent the solution set to the system of inequalities. Explain how you found the region to shade. We already did that to answer number 2 and number 3. I believe we have already done that. Yeah, there it is right there. Beautiful. Okay, so this double shaded region down here, that's called a feasible region because it meets both constraints. So, oh, here's some more constraints, feeding time and pampering time. Okay, so let's start from the beginning on this slide. Carlos and Clarita have been worried about space and startup costs for their pet sitter's business, but they realize they also have a limit on the number of time or the amount of time they have for taking care of the animals they board. To keep things fair, they have agreed on the following time constraints. Feeding time. Carlos and Clarita estimate that cats will require 6 minutes twice a day, morning and evening, to feed and clean their litter boxes for a total of 12 minutes per day. So that would be 12 times y, the number of cats. 12y, look at that. Now, dogs will require 10 minutes twice a day to feed and walk for a total of 20 minutes per day for each dog. So that's going to be 20 minutes per dog. That'd be 20 times x. So take your 12y and add 20 times x. All right. Now, how much time do we have? Looks like Carlos is going to take care of the feeding. So Carlos can spend up to 8 hours each day for the morning and evening feedings, but needs the middle of the day off for baseball practice and games. So he has up to, and we know up to means this expression for time has to be up to, which is less than or equal to 8 hours. Now this is a common mistake because some people would put 8 right here, but aren't the times on the left in minutes? So we're going to have to convert 8 hours to minutes. How many minutes are in 8 hours? Well, isn't there 60 minutes in 1 hour? So 60 times 8 would be what? Well, 6 times 8 is 48, so 60 times 8 would be 480 minutes. So there is our inequality in standard form for the constraint for feeding time. Oh, that's beautiful. Now, pampering time. The twins plan to spend 16 minutes each day brushing and petting each cat. All right, so that's 16 minutes times the number of cats that they are boarding. I'd say 16y. And 20 minutes each day bathing or playing with each dog. So dogs apparently need a little more time. That's 20 times x, the number of dogs. So let's go plus 20 times x. And now let's set up our inequality. How much time do we have to pamper our animals? All right. Clarita, it looks like Clarita will be our pamperer and Carlos is the feeder. Clarita needs time off in the morning for swim team and evening for her art class, but she can spend up to 8 hours during the middle of the day to pamper and play with the pets. So again, up to 8 hours. How did we do that for Carlos? Less than or equal to 480 minutes. We're going to do the same thing over here. Less than or equal to 480 minutes. And that is the inequality in standard form for our pampering time constraint. So we now have 2 more constraints to deal with. Write inequalities for each of these additional time constraints, which we already did. Shade the solution set for each constraint on separate coordinate grids. So they want these on separate coordinate grids. That's why I gave you all that graph paper earlier. So feeding time, 20x plus 12y is less than or equal to 480. Do you think we might want to start with a boundary line? And we're going to use our intercepts. So at x equals 0, I have my y-intercept, and at y equals 0, I have my x-intercept. So if x equals 0, I have 20 times 0 is 0, and I'm left with 12 times y is 480. So y would be 480 divided by 12. 480 divided by 12, and that's 40. Okay, now, if the y is 0, well, 12 times 0 is 0, and I'm left with 20 times x is 480. So to find the x, when y is 0, I just take 480 and I divide by 20. All right, I think that's 24, but let's double check. 480 divided by 20 is, yes, 24. So I have a y-intercept of 40. I'm going to have to estimate that one. 15, 30, 33, 36, 39. So I'm going to be about right there. And an x-intercept of 24, which I can see is exactly right here. So we break out our ruler and we look, equals, I need a solid line between those 2 points. And there's my boundary line for feeding time, for the feeding time constraint. Now, do you see that plus 12y? I already know we're going to shade below. But let's practice converting the slope intercept so we can see even more cool things. How about we subtract the 20x's from both sides? And less than or equal to will not be affected when we're subtracting. And the 20x minus 20x is gone, leaving 12y is, and I cannot combine these, so I have negative 20x plus 480. And now one more step. Let's divide both sides by 12, which means let's just divide every term by 12. 12 is positive, so my inequality symbol is not affected. And now let's cancel those factors of 12. And y is less than or equal to, oh, I skipped ahead a little bit, okay. So anyway, look at this over here. A negative divided by a positive is negative, And can I reduce 20 over 12? Well, what number goes into 20 and 12? The biggest number. And I think that would be 4. 4 goes into 20 5 times, and 4 goes into 12 3 times. So negative 5/3. And don't forget our factor of x. Plus, and what's 480 divided by 12? I'll punch that out. 480 divided by 12, and I'm getting 40 plus 40. And hey, that's the y-intercept we were expecting now, wasn't it? Oh, my battery is running low. You might want to plug in your PC. Okay, let's see if we can get through this. Okay, so here we go. Wish us luck. All right, so y is less than or equal to this boundary line right here. So I know I have to shade below. There it is right there. Okay, let's do the same thing for pampering time. All right, first, let's use intercepts to graph the boundary line. I think I'm speeding up a little bit because I'm worried about my battery. All right, and now let's put our x is 0 and y is 0. And if x is 0, I'm left with 16y is 480. So 480 divided by 16 is 30. The y-intercept is 30. When y is 0, 16 times y is gone, and I'm left with 20x equals 480. So let's go 480 divided by 20. And I've got a 24 right there. 24. So let's plot those. Hey, there's my y-intercept of 30. And look at this. There's my x-intercept of 24. I break out my ruler and draw a perfect line between those two intercepts. And now the 16, I think we're going to shade below. But let's subtract the 20x's. Does not affect our inequality. So 20x minus 20x is gone, and I have 16y is less than or equal to negative 20x plus 480. Now let's divide both sides or every term by 16. Okay, less than or equal to, because we divided by a positive, and the 16's cancel here, leaving the y is less than or equal to. A negative over a positive is negative. And can we reduce the fraction 20 over 16? Well, 4 goes into 20 5 times, and 4 goes into 16 4 times. So that would be negative 5 over 4, and don't forget that x. And then you have plus 480 divided by 16, and 480 divided by 16 is 30. All right, so here's my slope-intercept right there. Note the y-intercept of 30, and I've got a slope of negative 5 over 4. All right, so the key here is y is less than or equal to that boundary line, meaning we shade below. Right on. Okay, 5. Rewrite your systems of inequalities to include the additional constraints for feeding time and pampering time. So let's do them all right here. And remember our space constraint. 24x plus 6y is less than or equal to 360. Our cost constraint, 80x plus 32y is less than or equal to 1,280. Our feeding time constraint, 20x plus 12y is less than or equal to 480. And our pampering time constraint is 20x plus 16y is less than or equal to 480. Now this is a system. So all of these constraints we need to use to figure out how many dogs and cats that Carlos and Clarita can board. Wow. All right, but we can handle this. Okay, number 6. Find at least 5 combinations of cats and dogs that would satisfy all of the constraints represented by this new system of inequalities. How do you know these combinations work? Well, we have graphed all of these boundary lines throughout this unit right here, and you know that we need to be below every one of those boundary lines to meet all of the constraints. That gives us what we call a feasible region, which would be down in the bottom corner here, there, and there. Okay, these points satisfy all of the constraints. Well, there's a point And I'm going to use the same x values. There's a point, there's a point, there's a point, there's a point. Now, because all 5 of these points are below every boundary line, those points would work. And those ordered pairs would be the number of dogs and cats that Clarita and Carlos could board. So the x-coordinate on each of them would be 3. And the y-coordinate would be, and again, I'm going by 3, so what's that, a 12, 15, 18, 21, and 24. There you go. If Carlos and Clarita board 3 dogs, they have room for 12, 15, 18, 21, or 24 cats. And that includes cost, pampering time, feeding time, and space. Okay, so number 7, find at least 5 combinations of cats and dogs that would satisfy some of the constraints, but not all of them. For each combination, explain how you know it works for some inequalities, but not for others. Beautiful. So here is our same set of boundary lines for every constraint, and we found the 5 ordered pairs that would work. Do you notice that they're below all 5 boundary lines? Or excuse me, that's 4 boundary lines. All right, so to find ordered pairs that will work for some of the constraints but not all of the constraints, we just have to be, in between these lines somewhere. All right, so these points satisfy some of the constraints. Well, again, let's just think about our red boundary line right there and this stuff right here in the feasible region. These points cannot be in the feasible region. So maybe I go up a little higher. I could put my points up here somewhere. Let's see. Yeah, so I use an x is 3. And then how about if I use this point, this point, this point, this point, and I need one more. How about that point? Beautiful. Now, let's write those ordered pairs. So notice again, to keep my job as easy as possible, the number of dogs would be 3 for each of them. And now what's the corresponding y-coordinate for each of these points? Well, the y-coordinate at that bottom point there, see my arrow, would be 30, and then 33, and then 36, and then 39, and then 42. Now, these points satisfy some of the constraints, all right? Like this point up here satisfies this constraint right there. It's underneath that boundary line, but it does not satisfy the constraint that's underneath the red boundary line, all right? Some of the constraints, but not all of the constraints. Okay, now 8. Shade a region of the coordinate grid that would represent the solution set to the system of inequalities consisting of all 4 pet sitter constraints. We have already done that. Explain how you found the region to shade. So here it is right here, and here's the key. All right, we set up our system of inequalities, and every one of them were in standard form. And then we use intercepts to graph each boundary line. And then we talked about, well, all right, the constraints would be everything below every boundary line. So we chose 5 points that are below every boundary line, and that would be these 5 points right here. And that's because those 5 points are they are in what we call the feasible region. So this shaded region is the feasible region right there, meaning any ordered pair where my number of dogs and my number of cats are whole numbers would work if they were within this feasible region, including these solid boundary lines. Okay, now 9. Shade a region in quadrant 1 of the coordinate grid that represent all possible combinations of cats and dogs that satisfy the 4 pet sitter constraints This set of points is referred to as the feasible region. Hey, look at that. Since Carlos and Clarita can feasibly board any of the combinations of cats and dogs represented by the points in this region without exceeding any of their constraints on time, money, or space. Okay, time, money, or space. What about, pampering time and stuff like that? Oh, time is pampering and feeding. So that's, there you go. Okay, well, guess what? We have already done that too. All right, but now they said quadrant 1, and here's what they're thinking. They are thinking we were using an entire coordinate plane rather than just quadrant 1. All right. Now, we have done quadrant 1 the whole time because can the number of dogs be negative? That would be any point out here in quadrant 2 and quadrant 3. Can the number of cats ever be negative? And that would be any point here in quadrant 3 or quadrant 4. No. So we already did it, and we used quadrant 1 the entire time, and we said the feasible region would be those points right there. Feasible region. Okay. Now, I don't know, but I think our graph is way prettier. We don't need the entire coordinate plane because dogs cannot be negative. Yes, we might find a dog with a bad attitude, but we cannot have a negative number of dogs. Nor can cats be negative. Okay? Now, how is the feasible region shaded in number 9 different from the solution set to the system of inequalities shaded in number 8? Well, again, here's number 9. Just quadrant 1, and our number 8 looked like this. A much better graph in my mind right there. All right, but they apparently expected you to just have your boundary lines go through the intercepts and use the entire plane. And again, that is irrelevant because our number of dogs cannot be negative and the number of cats cannot be negative. So this is the feasible region right there in quadrant 1, and we zoomed in and we took out the negative cats and the negative dogs from the beginning. I hope you guys enjoyed this. I had a ball putting this one together. I'm sorry I lost power in the middle of it, but we're doing our best. And here comes more disruptions. So, today it was just one of those days. We had a storm last night. Wi-Fi was rough. I lost my signal in my first 2 classes today, and then I came out to work in the living room so I'd be closer to the Wi-Fi, and it actually worked. I did a great pre-calculus lesson for 6th period today, and then I just continued to be out here in my living room recording. But with that, we had to deal with dogs, phones, and so on. But I hope it went well. You guys, let's get that ready, set, go for which section is this again? 5.5, I think. All right, and have a great day. Call me, email me if you have any questions.